Well, good afternoon. I'd like to welcome everyone to the latest in the WIRE's webinar series on advanced technologies. And with us today, we have MetOx, who's going to be talking about superconductors and their applications for the grid. And we're very pleased to have from MetOx with us Bud Vos, who's the CEO of MetOx, Marie Hayden, who's the Senior Vice President for Development, and Jay Vaitha, Vice President of Strategy and Business Development. For those of you who are watching today, we do have the opportunity for folks to submit questions. And I would encourage you to think about questions you might have for our folks from MetOx as they go through the presentation. If you type your question in through the question function, which is in the box on the right hand of your screen, I'll be able to have that question and I can present them the question once we get through their presentations. So again, please think about any questions you might have for our presenters today, and we'll be happy to tee them up for them to respond to. So with that, I'm going to go ahead and turn it over to you folks at MetOx, and we're all anxious to hear more about superconductors.
Fantastic. Thank you, Larry. Really appreciate the introduction and appreciate the opportunity to be here today, meeting with all of you. Jay is going to be running us bringing the slide presentation up, but I just wanted to briefly talk to you a little bit about MetOx and introduce you to this world of superconductors. We've titled this talk Solving Grid Challenges with Superconductors, and Marie and Jay are going to take the group through a number of use cases, examples, and reasons why superconductors really are a key element in solving tremendous grid challenges that we're faced through the energy transition. Many of you may know that this type of technology has been around for a while, but hasn't really reached total mainstream. And one of those key reasons why is because of the cost profile and the competitive nature of being able to deploy this technology at scale. And MetOx as a company is fundamentally driven around how do we bring superconductor technology to a scale that we can deploy it broadly across different segments of the grid and various applications. We do have some very exciting news. Yesterday, we announced a brand new funding round, which we just concluded with some wonderful investment partners. You can check that out on our website. And you'll of course get links to the rest of this presentation as well and other materials through the WIRES folks. And then you can find us on social media, on LinkedIn, and you can find that press release. Very amazing technology that we're bringing to bear. And with that, I am going to turn the floor over to my colleagues who are going to begin to take you through this amazing story of what superconductors can do to solve amazing grid challenges. Marie and Jay?
Sure. My name is Jay Vaitha. As Larry mentioned, I'm the VP of Strategy here at MetOx, and I'll have Marie introduce herself when she gives her session in the middle here on grid applications. I'll be taking the group through an introduction to superconductivity. As I mentioned, Marie will talk through grid applications, and then Bud will jump back in at the end and discuss partnering with MetOx and how you guys can join the growing ecosystem of superconductivity partners. First, we'll begin with an introduction to superconductors, and superconductors are materials that, when cooled to a certain critical temperature, actually no longer exhibit the property of resistance, which allows for very high current flow and strong magnetic fields to be created using those substances. You might remember a kind of high school or college physics experiment where they were able to make a little ceramic float using liquid nitrogen over a magnet. This is demonstrating the property of superconductivity. MetOx manufactures a superconductor in a form that's useful to create devices. This form is a wire, which you can see on the right-hand side of the screen here. The wire is either 4 millimeter or 12 millimeter wide. The example there is 12 millimeters. It's a nickel alloy substrate, and the superconducting layer is deposited onto that layer. And that superconductor is only between 1 and 2 microns thick, and this 12 millimeter wire carries over 600 amps of current. What we then do with the wire is we sell into different device manufacturers. The largest and most relevant for this audience is cable manufacturers for the transmission and distribution grid, as well as some OEMs who manufacture grid devices such as transformers and fault current limiters. We also sell to magnet winding customers who use those magnets for things like nuclear fusion, pilot reactors, MRI machines, and other types of high magnetic field devices. And then we also will be able to serve into devices such as rotating equipment and wind turbines and things of that nature with our performance wire. Our product XEUS is a better conductor than copper wire and has kind of two main properties that make it a very efficient conductor. The first is that high current density that's enabled because there's no resistance when the superconductor is cooled below that critical temperature. The superconductor that we use has a critical temperature of 77 Kelvin, which is the temperature of liquid nitrogen used as the coolant. At that temperature, there's zero electrical resistance, which results in no line loss in cables manufactured with superconductors. Those cables can carry up to 10 times the power equivalent of equivalent copper cables because the wire actually carries 250 to 600 times more current than copper on a cross-sectional area basis. And you can see in the photo there just the comparison of what a copper wire cross-sectional area would look like versus a superconducting tape. I won't go through everything on the timeline here, but it's important to note that superconductors have actually been around for a while. In their first iteration, low temperature superconductors, they actually required liquid helium, and several Nobel Prizes were awarded for the discoveries of those materials. Those materials are still used today in devices like MRI machines. And if you're familiar with the ITER fusion project in France, that's using low temperature superconductors. Around the late 80s, they started to develop high temperature superconductors, which work with liquid nitrogen rather than liquid helium, a much more available coolant. And since then, there have actually been several examples of deployed superconducting cables in electricity grids, some even by wires members. And we've highlighted several of them here. The first of which that was a grid connected HTS cable was done by Nexans and AMSC and LIPA in 2008. Since then, there have been several other projects that have been announced. And one of the things that MetOx is most excited about is launching our product XEUS wire to the market in 2023 so that we can begin to supply the cable manufacturers who build these cables. The question of why are we excited about HTS now has come up a lot. The technology, like we mentioned, has been around for a long time. Those early pilot projects were done almost 20 years ago. And the reason that it didn't take off then has to do with what Bud mentioned earlier about the cost profile at that time, and also the challenges that the grid was facing at that time. You know, at that time, we didn't have a projection of electrifying an additional 40% of our end energy consumption. We didn't have the demand for increased renewables that all of the wires members are seeing on their grids. We didn't have the proliferation of electric vehicles driving up the forecasted demand going forward. And lastly, in the HTS segment, we didn't have other markets that were putting price pressure on suppliers to actually drive the cost of superconductors down. Now we do with the advent of nuclear fusion. There are many companies, over 40 nuclear fusion companies that have raised close to $7 billion so far to do pilot demonstration reactors, which require superconducting wire. And as a result, we've seen price come down to a point where these projects in the grid space can actually be competitive with other conventional transmission and distribution alternatives because the price of the conductor has been driven down. We also wanted to take a moment to just note, while we don't expect to run out of copper this year, the volume of copper required to meet net zero demand by 2050, according to IEA and USGS, is actually twice the amount of copper we've mined throughout all of human history. So I think we are unlikely to mine twice the copper of all of human history in just the next 27 years. And that's why we believe alternative conductor technologies like superconductors can make a big difference in the transmission and distribution space. The graph on the right from S&P Global shows the energy transition broken down by segment and refined copper usage. And if you'll notice, the light green bar at the bottom is for transmission distribution. It's the largest consumer of copper in the energy transmission and energy transition segment in almost every 5-year period, with the one exception of 2035 at kind of peak EV and charging adoption. So again, transmission distribution is copper intensive, and alternative conductor technologies can carry more power with less loss using less resources. And that's really the key benefit of using superconductors in grid cables. We're able to carry transmission level power at distribution level voltages. And these products are already commercially available. We've highlighted the cable products from 2 of the suppliers of superconducting cables, both LS Cable and Nexans. You'll notice in these designs, they've got 3-phase concentric designs where they have all 3 phases in a single cable. This enables the reduction of land needed to lay cables, as well as optimization of right-of-way. These cables, as mentioned, due to superconductivity, have near zero line loss and also don't have any EMF emission. They can reduce or even potentially eliminate the need for substations or transformers, because you're able to move that high power capacity at that kind of medium to low level voltage. And these cables are available in both AC and DC capacities today. And so with that, I'll turn it over to Marie, who's going to discuss existing grid applications of superconductors.
Great, thank you so much, Jay, and thanks everybody for joining us on the webinar today. Jay has just done a great job, I think, explaining how superconductivity works. And I'm going to talk a bit about how we can apply superconducting materials for the transmission and distribution of electricity in our grids. I'm going to touch on some of the applications and use cases we see today, and I'll also give you an insight into some of the product development that's going on with the big manufacturers, both in cables and other technologies, for future application of HTS. So Jay did describe the key properties of superconducting material. I'm just going to re-emphasize them here again, because I want you to think of them in the context of how you design and operate your electricity grid. So the most important principle here is that superconducting materials, when they are supercooled, have zero electrical resistance. So think a bit about that. If you look at how our grids have evolved over the last 50, 60, 70 years, as we needed to transfer more power across our grids, we found ourselves increasing the voltage level at which we did that. And the reason we did that was because by increasing voltage, we could reduce the amount of current going through the line, and we could reduce the I²R losses going through the line. And even though our infrastructure was more expensive when we went to higher voltages, and our switchgear was more expensive, and of course the right-of-way was much bigger with high voltage lines, this was still more than compensated for by the reduction of I²R losses. So this is how our grids have evolved to date. But if you think about it now, with materials like high temperature superconductors, if they don't have any I²R losses, we can actually step back and think a bit about how we design our grid a little differently. So by having no I²R losses, we can transmit a lot more power at lower voltages than we do today. And when you're operating at lower voltages, of course, you've got smaller cables and smaller rights of way and lower substation equipment costs as well. Not to mention that reducing the I²R losses has a lifetime benefit as well, a lower operating cost, and of course avoids the waste of energy. Another feature of these cables, which we've mentioned a few times, is that they are supercooled. In fact, we operate these cables at -200 degrees centigrade, and that is achieved by circulating liquid nitrogen through them. Of course, one of the benefits of that as well is that you don't have any thermal spacing requirements when you're installing your cables, because there's no heat dissipation from the cables. So if you think about installing a 3-phase cable today, you would be used to seeing the cables separated by a certain distance, and most of that is to do with thermal dissipation. And again, when you have HTS cables, you don't have to worry about that. So not only are you installing a lower voltage cable, but you can also install them in a much more compact design. And so these two benefits really allow us to dramatically reduce the right-of-way required. And we all know that today installing high voltage equipment and high voltage lines is very challenging from a siting, a permitting, and a public acceptance perspective. So reducing and narrowing these rights of way obviously has a lot of benefits. I'm just going to ask Jay just to move us on to the next slide. Thank you, Jay. There are, not surprisingly, a number of applications which take advantage of this feature today. And the one you'll see the most of is really the installation of HTS cables in congested urban networks. And I have a couple of slides going through use cases on that, so I'll explain that in more detail in the next few slides. I'm also going to talk briefly about fault current management. I'm sure many of you have come across fault current limiters in your work before. Superconducting materials are really perfect for fault current limiting devices because these superconducting tapes, this HTS tape, once the current exceeds a particular threshold and once the temperature exceeds a particular threshold, they go from having zero electrical resistance to very high electrical resistance. So they're effectively invisible to the grid under normal operating circumstances, but under fault conditions, they act like a really big resistor in the middle of the grid. And that will dramatically reduce the fault current in a substation or in an area and can reduce the level of voltage drop we see during faults as well. So fault current limiters are another great application of high temperature superconductors that are being deployed today. And it goes without saying that when you can transfer large amounts of power over smaller voltages and with smaller rights of way, it's instantly easier to start connecting in remote renewable generation parks and start connecting in the very high capacity electric vehicle stations and of course the data centers as well. So that all falls out of these same properties which I've just discussed. And Jay, I'll just go on to the next slide where I talk about the first use case of HTS that I picked. I should say here is a quick table that gives a list of some of the HTS projects that have been deployed around the world. Jay has already mentioned that we've been seeing these projects deployed since the mid-2000s. So it was about 20 years after the discovery of high temperature superconductor materials that we saw the beginning of deployment of high temperature superconducting cables. And over this last period of the last 10 to 15 years, there have been really good pilot projects, lessons learned, and developments in the technology. And the projects that we see now at the lower end of this table are projects which are going in because they're commercially viable projects. And we've gone past the pilot phase and the pilot project phase of this technology. One thing you will notice is that we have a lot of different voltage levels and a lot of different MVA. So a lot of different cable designs are out there. Jay mentioned a lot of the cable manufacturers today have a HTS product division. So you'll be familiar with companies like Nexans. They're the biggest or second biggest high voltage cable supplier in the world, and they have a large HTS division. But as do companies like LS Cable in Korea and NKT Cables in Denmark. And so when we look at this, the other thing you might notice is that the length of these cables tends to be quite short. This is not a technical limitation on HTS cables, but it has been driven by two things in the past. The first being that, of course, a lot of these early projects were pilot projects, so typically we'll do pilot projects over smaller lengths. But also, as Jay and Bud mentioned, the capacity, the availability of the HTS wire that companies like MetOx makes has been quite limited over the last 10 to 20 years. And it's great to see companies like MetOx really scaling production capacity now to be able to serve the electricity and transmission and distribution markets. I'll move on actually now to the next slide and just talk briefly through one of the projects in Korea. So this is the Shingal project in Korea, which was a partnership between LS Cable Systems and KEPCO. KEPCO would be the transmission operator in Korea, in South Korea. And this is just a very good example of where we see a lot of the applications around the world. What we're looking at here is a network that's 154 kV transmission network and a distribution network of 23 kV. And the need here was to bring additional supply into the Shingal station from the Hongdae station. And the original plan was to put in a third 154 kV cable and then add in additional transformer capacity at Shingal. But the right-of-way between the two stations and the substation space at Shingal were both extremely constrained, and they just couldn't do this project that way. So that's how they ended up looking at the high-temperature superconductor application. And instead what they did was they installed a 23 kV cable. I think Jay showed a picture of that exact cable earlier on. much smaller right away, a much smaller and faster installation project. They connected at the 23 kV level, and they provided the additional transformer capacity at Hongdijk where there was space, rather than at Qingdao where there wasn't. So this is an absolute classic use case of HTS today. It's something we see all around the world. And what we're seeing now is that these projects are yielding actual cost competitive savings. In this case, this project was 22% cheaper than the equivalent copper 154 kV cable project. And it has triggered additional projects in Korea, including the Munsan project, which was installed this year. So if we move on, I'll gladly take questions on this at the end, and there are links to these projects on these slides as well, so you can find out more information that way. Just highlighting Ampacity in Essen in Germany. It's a 10 kV, 40 MVA project, 1 kilometer, and it was installed in 2013, and it's been the longest serving HTS cable that I'm aware of, at least, that's been in continuous operation, and it has been very successful in continuous operation with no faults and no issues, no interruption to its operation during that period of time. One of the great things about having these cables super cooled is that they don't go through the heating and cooling cycles that you get with traditional cables. So they don't have the same level of wear and tear that you would associate with more traditional copper and aluminum cables. This application is almost identical to the last one, so I don't think I'll actually go into it in any more detail. I just wanted to highlight this project in Germany because it has been in service for such a long period of time. Bringing it closer to home, and when I say home, I mean the US. My home is actually in Ireland, in case you hadn't detected the accent. I'm coming to you from Dublin. But closer to home in the US, ComEd are probably the most recent installation of a HTS cable. This took place in Chicago in 2020 and 2021. This was a partnership between American Superconductors, Nexans, and ComEd. And in this case, what they were doing was linking two adjacent substations with a superconducting, very high capacity cable. And effectively, this link was going to provide a backup from one substation to the other. So in case of the loss of the infeed to substation A, it could be actually supplied from substation B. And this was considered to be a resilience project, and it was sponsored by the Department of Homeland Security's as an initiative in securing the US grid against extreme weather and catastrophic events. As I say, this was installed in 2020 and put into service in 2021. And lastly, I just wanted to give you a reference project in terms of the superconducting fault current limiters that I mentioned earlier on. The most recent one and largest one that I'm aware of is the 220 kV installation in Moscow. This is a 1200 nominal current SFCL, so normal operating conditions. That's the kind of current that would flow through this with no change and no resistance. Once you get a fault, and a fault ending up to 50 kiloamps, you go into this very high resistance gets injected into this location. So this was installed in 2019. One of the key things they were trying to do was avoid big voltage reductions during fault currents, during faults, I should say. And you can see in this chart, the blue columns represent retained voltage during a fault, and you can see how much of that voltage is retained during the fault. And I'm sure many of you will be familiar with how important it is to try and keep your retained voltage levels high to avoid interruptions to industrial processes, or in fact causing generators in the area to go unstable. And that's one of the big use cases for the Moscow superconducting fault current limiter, and that has been in service since 2019. So moving on now, and just to give you a little glimpse into some of the products which are under advanced development and coming at us at speed. HTS transformers, very, very great application of high temperature superconductors. Instead of using copper, we use HTS. That allows us to design smaller and lighter transformers that are easier to install and easier to ship. And also, of course, they don't use oil. So we get rid of the hazard associated with having oil-filled transformers, whether that's environmental damage or fire risk. And again, a really positive application of HTS transformers. We expect to see HTS transformers hitting the shelves, so to speak, in about 3 to 5 years. And a number of companies are looking at developing these, and these will be household name companies. So if it's something you're interested in, we'd be very happy to facilitate that discussion. Another interesting one is with Veer. So Veer is a company located up in Boston, and they're developing overhead line HTS superconducting lines. Everything to date has been underground cables because of the need to circulate that liquid nitrogen, and how that's done is more suited today to underground cables. But FERC have been working on a way of doing this with overhead lines. So there's a really exciting set of developments going there. And I have a slide just coming up now on offshore cables, because I know offshore grids is all the rage right now, and it's a perfect application for HTS. So all the big manufacturers who have HTS products are all turning their attention and developing offshore HVDC HTS cables, and I'll talk about that now. And we might go on to the next slide, Jay, and I think this is probably my last slide. So just on that, as I say, you know, with HVDC, we've no AC losses, and obviously with HTS, we've no ohmic losses. So this combination makes the high temperature superconductors really perfect for use in HVDC. Nexans have qualified a 320 kV, 3.2 gigawatt HVDC cable. And again, Supernode, another company you might not be as familiar with, but they're developing a HTS technology for powering what they call a super grid, which would be an onshore and offshore super grid around Europe. So there's a huge amount of work going on and product development going on in the offshore space. And I've no doubt that into the future, we're going to move away completely from having copper cables in the sea to HTS cables, just because they make so much more economic sense, and also take us a little bit away from that copper dependency, which Jay mentioned earlier on. One of the great things, again, is this reduction in the number of cables you need to transmit high levels of power. There's a good picture there of one of these cable laying ships. These ships are in scarce supply, and as there's a global race on to install offshore renewable energy, availability of ships like this for doing installations can be a 3, 4, 5 year lead time. So obviously, if you can reduce the number of cables you have to install, there's a significant benefit there. And the very last thing I'll just mention as well is that I know when we think about offshore grids, we do think about DC connections, but in some cases, the offshore wind is not that far offshore. It might be 10, 20, 30 kilometers offshore. And it could make sense in some cases to connect that with an AC cable instead of a DC cable. I've mentioned LS cables a few times in Korea. They have a land cable, a 154 kV land cable that can carry 1 gigawatt. No reason why that couldn't become a submarine cable. So I could see a time where, you know, the supply chain crunch we're seeing around converter stations, and the concerns people have about controller interaction with HVDC as well, could see some of these offshore wind parks actually get connected at AC instead of DC. And again, HTS is the way that can happen. So I think, Jay, that's my last slide. I've probably gone twice as long as I meant to. Apologies for that. And I'm happy to hand back now to Bud, who will tell you a little bit more about MetOx and MetOx's role in this supply chain.
Thank you very much, Marie. Really appreciate that. I think you can see from all of that discussion, there's a vast number of use cases and capabilities that we can bring to bear using this type of technology. So, but let me tell you a little bit about MetOx. We decided to close the presentation with this discussion around how do you partner with us? If you're a member of the audience and you want to learn more, and you want to see how this technology can impact what you're doing every day in terms of your grids and your deployment of technology for energy transformation, how do you work with us? So the first thing is that a little bit about the company. So it's been a long time of R&D and science that's brought us to this point where we're now scaling this technology. We're a very strong company, 70 employees. As we mentioned, we just closed some additional financing, which was announced just yesterday. Strong IP portfolio, and we do operate out of Houston, Texas. And then we have this plan for production in terms of scaling this technology from 1,000 kilometers a year of tape to 10,000, and then growing even beyond that, and perhaps even much larger than that. Next slide for us, Jay. The technology we've been talking about here is fundamentally based on, as we call it, a superconductor technology, but it's not the easiest thing in the world to manufacture. And again, you're welcome to visit us in Houston and actually see how we manufacture this. These are the various layers that go into that manufacturing process. And if you'd like to learn more about these layers, you're welcome to meet and greet with us. But I think what's important to note is that all of this technology, we have to perform just like a normal cable. So when this tape or material is ultimately delivered to a cable manufacturer, we have to adhere to the same specifications and the same requirements around things like bend radiuses and tensions and all of those aspects, not just this vast current carrying capacity, but also the mechanical specifications as well, because those cables have to live the same life as a traditional copper cable. And ultimately, this technology not only allows us to do that, but then allows us to deliver this high grade of 250 times the amount of power that you can in traditional copper in this very small package, but we still have to perform like a traditional copper cable mechanically. If you can go to the next slide for us, Jay. This is our rollout plan. You'll see us talk about these projects, and we'll be talking a lot more about these over time as we build out our first line, which is coming live literally as we speak. On this call, we are launching this line. This will be the largest HTS manufacturing facility in North America, and it's literally weeks away from launching. We'll then be moving into an expansion of that, and then an additional expansion even beyond that. And the reason for this is ultimately cost driven, but also it's demand driven. We see a vast demand in this marketplace. And as we're able to both drive the cost down and increase the scale of our technology, which we've proven we're able to do, we can bring much more product to the marketplace, which is what we believe will happen as we go from these early demonstrations and projects of cabling projects and fault current limiters and these types of devices. We believe that we will see this vastly deployed due to the factors that Jay was referring to earlier in terms of the grid transformation needs, the power needs, as well as the environmental footprint. You can go to the next slide for me, Jay. So speaking of the environmental footprint, frankly, no other technology has the benefit profile of something like HTS and what we're producing. Not only can we bring this technology to bear and expand the grid capacity through power, we can transmit renewable energy, use it for large interconnectors. We can talk about offshore use cases, as Marie said. We can do this all while reducing our reliance on copper. And we believe at MetOx that it's better to let copper go where copper needs to go. Things like cars, batteries, other types of devices, and let's transform the grid with technologies such as this, where we can leverage existing right-of-ways, existing capabilities or throughways, existing underground infrastructure. We can leverage those passageways, so to speak, deploy new technology in it, and ultimately deliver a much higher, more reliable grid, much higher capacity, much more reliable grid. Next slide. So how do you partner with us? With that little bit of introduction in terms of where we are and how big we are and where we're transforming to, we get this question a lot from utilities and grid operators and power producers all around the world. So we like to start with what we call a workshop, where we identify opportunities along with you for where you can use HTS to solve various grid challenges. You might have some very specific use cases in mind. You might have some very specific projects in mind, but we often start with this idea of let's explore the possible and imagine the possible in terms of what it is we're able to do. We also are building a vast ecosystem of cable manufacturers, device manufacturers, equipment suppliers, and OEMs all around the world. We'll actually bring those parties to the table, and we'll bring those to those meetings and those discussions so that we can then bring that ecosystem together to deliver a full joint project for you. It's not just about the HTS technology. It's not just about the cable. You've got to work through the interconnection. You've got to work through the other technologies that are required to deploy in these projects. So we believe in this ecosystem approach, and that's what MetOx is here to do, is to help facilitate that and bring all the parties to the table that allow us to ultimately work together to then identify how we can solve some of these significant challenges. I think the next slide actually has a brief overview of what that workshop generally looks like. It's usually a 2-day type of workshop, and we will sit with you and your team, and we'll take you through various elements of these use cases, these capabilities, give you a brief tutorial on superconductors, go dive deep on some of the technology, even talk about what are some of the competitive technologies that are out in the world, and bring all of those together so that day 2, we can then talk about what could be possible. We learn more about your grid, we learn more about your challenges, learn more about where you might be looking and thinking their solutions, so that we can conclude that workshop with an action plan that would allow us to then work together to either identify or dig deeper on projects, and then really begin to start figuring out how could we deploy this technology and frankly put you ahead of the rest of the game, so to speak, in terms of being able to do that with our partners and with ourselves being the supplier of some of the fundamental technology. With that, I'm going to conclude our part of the discussion. I would say, please join us in rewiring the world for net zero. We do believe this is just the beginning of what HTS can ultimately bring to the world. I'm very, very happy to have Marie and Jay here to continue to answer questions that you may have, as well as just to learn more about MetOx. Feel free to reach out to us, and we'd be happy to schedule follow-up discussions, calls, and interactions as needed. Larry, I'll turn it back over to you, sir.
Well, great. Thank you, Bud and Marie and Jay. That was a really interesting presentation. And I want to remind our viewers, if they have any questions, please go ahead and feel free to put those into the question box. And I'll be happy to go through those. But in the meantime, I have a few questions that occurred to me as you were going through the presentation. And I thought I'd put them out there to give you the opportunity to respond or clarify some things. Marie, I want to start with you because you talked a little bit about existing rights of way issues. I wanted to ask you a little bit more on that. Are there any regulatory hurdles to cross with using HTS wire on the existing rights of way that we have here in the US?
Hi, Larry. No, there are no regulatory hurdles there. I mean, effectively, as I say, most of the high temperature superconductors today are being installed as underground cables going into either directly buried or into tunnels. And again, there are no regulatory issues here or in the US. The liquid nitrogen product, which is used to cool and circulate through the cables, that's an extremely safe product. And if there is a leak, if it does somehow or another, if there's a dig into the cable, the liquid nitrogen actually just vaporizes into air. And as you would know, like 80% of air is made up of nitrogen, so there's nothing harmful there. And I think I'd go on to say, when we talk about regulatory rules around superconductors, it's worth highlighting that superconductors have been identified by FERC and the Department of Energy as an advanced superconductor, an advanced conductor to be used in the transition to net zero. And FERC Order 2023, which talks about interconnection and using advanced technologies, also includes HTS superconductors. So I would say, in fact, the regulatory environment is very positive for superconductors, if anything.
Oh, thank you. And yeah, you actually mentioned DOE. I was also going to raise a question about DOE and some of support and funding opportunities from the different DOE programs that are out there. Does the DOE Grid Resilience and Innovation Partnership Program, or the GRIP program, support this technology rollout in any ways that our attendees should be aware of?
Yeah, I'll hand over to you for that one. Jay is our expert in this area.
Yeah, for sure. Superconductors are an advanced conductor technology that would be included in innovative grid projects that would be covered under GRIP applications. And so for utilities that are looking to submit those, I know there's a round that has a concept paper deadline of January 12th. If you're interested in potentially scoping out a concept paper, we'd be happy to do that for either this round or the upcoming one that will happen later in 2024.
Yeah, it sounds like that one's coming up pretty fast if you're talking January 12th. Another question I wanted to ask you about is, I know you're looking to scale this technology significantly in the next few years. Can you talk about or elaborate more on any of the major obstacles to adoption of HTS wire?
Certainly, Larry. I think, obviously MetOx is scaling its production facility to be able to supply the very big increase in demand we see for HTS amongst transmission and distribution, but also in other sectors like fusion and medical devices. So there's a very, very cross-sectoral demand for HTS, and there are no major concerns with scaling the production capability, and certainly things like the raw materials. None of these raw materials come with sort of critical supply chain shortages. None of them are hard to come by. We often have US supply of them, and most of them we use in very small quantities, going back to Jay's presentation at the beginning where we showed, just how tiny these HTS superconductors actually are. So we don't have any sort of scaling up issues there. I think when we talk about adoption, all technologies go through a fairly lengthy adoption cycle, particularly in electricity, transmission and distribution, where, we need to kind of step through pilot projects and make sure everybody has the technical assurance and knowledge they need to be able to own and operate and maintain new infrastructure. So that adoption pace is always a little bit challenging to predict how quickly a new technology will take off in the electricity sector. So we're kind of very encouraged to see the number of companies and the global dispersion of HTS projects, and the companies that we're supplying to are also seeing a strong demand for these into the future as well. So I suppose I would say to this audience, it's really good if you can collaborate when you're looking at doing pilot projects on new technology. So rather than each utility doing its own project, maybe coming together and at least sharing the lessons learned with each other, so that we don't end up in this kind of death by pilot, which can happen quite a lot with new technologies.
Well, I'm starting to get a couple of questions come in. I want to turn to a couple of those right now. And this touches a little bit on something you mentioned there about the production issues. And the question is the new production line specifically supporting conductor for utility applications, or is that production facility supporting other industry applications as well?
So that line will support several industry applications. However, we do anticipate that the cable wire product to be one of the main products coming off of that line. And so we are looking closely at all of the utility applications as we bring that line live.
And then another question that came is what kind of equipment is needed on either end of a cable for maintaining the liquid nitrogen system? Are there length limitations where some kind of booster station will be required along the length of a cable?
Yeah, that's a very good question. So there are a few different types of designs of cooling systems that are used with HTS cables, and each cable manufacturer tends to have their own version of the design. But what is common is that there is a length limitation that after every sort of 5 or 10 kilometers, depending on the cable and the supplier and the design, you do need some sort of intermediate station where you can sort of do additional pumping and pressurization of the liquid nitrogen to keep it circulating and keep it cool. So typically what we would say is up to 10 kilometers can be easily handled with refrigeration equipment at both substations. Once you go over 10 kilometers, you may need to have an intermediate substation along the way, or not a substation, but just a sort of an installation for additional pumping and circulation equipment. So that's what's expected there. That is an area, I will say, where when I talked about future products and I talked about the offshore grids, a huge amount of that research is in how do we go further and further and further with these refrigeration systems so that we can do longer lengths of cables.
And then I got another question, and this is a pretty general one, but it asks if you're curious about the use of superconductors in overhead transmission lines. And I guess they would like to hear you talk a little bit more about where things are with that and explain what's going on with it.
Sure, I'm happy to talk about that. RJ, do you want to talk about it? You're very familiar with the VEER team as well.
Yeah, sure. So there's a good partner of ours, a US company called VEER, who's looking at developing superconducting overhead lines. And obviously, this will open the market up tremendously to transmission and distribution projects, from the underground pilots that have been done today and commercial projects that have been done today to commercial overhead lines. And that's something that we're partnering with them on and are really excited to bring those projects forward and be able to eventually serve in the overhead market. The key challenge and their innovation is around the overhead cooling system. And so that's what their technology is.
And Larry, I might just add to that, to what Jay was saying. What VEER are really specializing in is how do you cool with liquid nitrogen overhead. But just for anybody who's trying to picture what it looks like, we are talking here about effectively an overhead cable. So it's not an overhead bare conductor, it's like an overhead cable. But because the superconducting material is so small and so light, you can actually support those cables off overhead infrastructure in a way that you couldn't imagine doing with your classic XLPE 220 kV underground cable, right?
Oh, great, thanks. I'm glad you touched on that. Actually, I was kind of curious about what the differential is between the weight from traditional wires versus superconductor wiring for something like that, but the implications could be for the infrastructure to support that. So Actually, another question along that line I was curious about too, because I saw you were talking about possibility of using HTS transformers in lieu of traditional transformers. Can you talk about what some of the differences are between the two? And like cost differential, what's the cost differential between this type of a new HTS transformer versus a traditional one?
Yeah, so the transformers are in the product development stage at this time, so I don't really have any good cost information on them. While they're stabilizing, there's a whole lot of different ways you can design the HTS windings, and they all have different impacts on things like, you know, eddy currents and AC losses and issues like that. So whilst the transformer manufacturers are trying to kind of arrive at the optimum design, we don't have good insight into where these are coming through in terms of price points. I do know that some of the manufacturers are particularly targeting are thinking about smaller transformers, like generator transformers for offshore wind turbines, for example, where weight, you know, lightweight is such an added value, if you like, having a lightweight product offshore, because it just totally reduces the cost of foundation, transport, and everything. So I think that's possibly where we'll see the initial products develop, but it's difficult for us to say because we're not actually right there doing the design. So I don't know if that answers your question or not. It answers it possibly as best as I can. I think James has something.
One thing that I'd quickly just add to that is, you know, I've spoken, you know, at the wires meetings to several members who are concerned about the lead times for conventional transformers, and that is one of the pressures that has these OEMs focused on alternative transformer technologies. So while, you know, we know it's taking a long time to develop transformers, they're also looking at new types of transformers to help support that market, because the demand for them is far outstripping supply right now.
Thanks. Another question came in there that's curious about finding out a little bit more about some of the installation and maintenance issues associated with HTS wires. Can you elaborate on some of those for a little bit?
Yeah, so the cable manufacturers have actually designed these superconducting cables to kind of be a drop-in replacement for conventional underground cables. So from an installation perspective, much of the same equipment can be utilized. They also kind of provide the cable cooling and operations and maintenance monitoring systems as a turnkey solution to the customer, so that all of that can kind of be done with the one partner and the one vendor there. So that makes it easier to maintain. The last thing that I'll add is much of the maintenance on conventional conductors is due to heat-related degradation, which obviously these cables don't have, given that they're super cooled. And so that's another kind of benefit of using this type of cable, which we actually anticipate and have seen from the existing projects, that there are lower operations and maintenance costs versus conventional conductors.
I can tell I've got a lot of like operations folks and engineers listening in on this, because some of these questions are really good, but they're very technical. I've got another one that came in, and this is in conjunction with the overhead transmission, but they're asking about, I'm gonna have to read this one. So for traditional overhead transmission lines are terminated periodically at dead ends. The tension is held by either a fitting that is compressed, crushed, or bolted very tightly. And I want to know, how would this work with having a liquid that has to be pumped through the line?
So very good question. I think I might have to take that one offline and bring in our partners Vera on the details of how they actually do those terminations and those joints between over across the different lengths. I know that they do have the sort of the cooling equipment is installed on the tower every X number of towers, and I'm sure it's related to where they connect that cooling equipment back into the circuit, and I'm sure it's to do with that, but I actually don't know the details of that design. So I'd love to answer it. It's a great question.
Okay. Do you have contact information on the slide deck?
Yes,
we have our contact.
We'll include that.
Okay, great. Okay, because we can we can post that as part of the presentation so people can follow up on some of these questions. I got another one that says, can you comment on companies like AMSC? Are they a competitor, or do you supply conductor for them? And they had developed turnkey solutions says it seems like MetOx focuses specifically on the HTS conductor production. Is that correct?
Yeah, that's right. So MetOx is focused entirely on manufacturing HTS wire, and we supply into a number of different companies. AMSC have wire production capability, but also are device designers as well. So they design products that use HTS, whereas we don't. We just design the HTS tape, and then we work with suppliers. I will say that there's a very good sense of collaboration and partnership in the industry of superconductivity. We're all very interested in seeing everybody grow because we recognize the importance of this technology, and people will not adopt the technology if there's only one supplier out there and there aren't multiple suppliers. So, you know, we have really good partnerships with companies like AMSC and other manufacturers of HTS. They are competitors, but we also are collaborators.
I wanted to follow up with a bit of a departure from the transmission side. Can you talk a little bit more about HTS's potential on the generation side with fusion generation?
Yeah, for sure. So fusion has really caused the increase in supply globally of superconductors. I'll give you some scale. One demo reactor from Commonwealth Fusion, the largest fusion company, requires 10,000 kilometers of HTS wire, and the global production capacity is less than 5,000 kilometers per year. So that just gives you the scale that's required, and that's just one of the 40 fusion companies that are attempting to build these demonstration reactors. What the fusion companies are using the wire for is actually to wind the magnets that actually confine the fusion reaction in those generators. And so they absolutely require the wire in order to create those strong magnetic fields, which is one of those properties that I discussed in the beginning of superconductivity that you are much better able to do with our products with high temperature superconducting wire than you are with low temperature superconducting wire, the previous generation of the technology, which required that liquid helium coolant, which is much harder to get, much more expensive, and ends up creating devices that are much larger. And so this creates kind of the more scaled down compact fusion reactors that we do expect and hope will be serving generation onto the grids in the 2030s.
Apparently, I'm not the only one interested in finding out more about the HTS transformers, because I got a question that says, what TRL is the HTS transformer at, and are they ready for a demonstration? What voltage levels and kVA? So.
Yeah, so these are probably in the earlier TRLs, probably the TRL 4-5 type level. We work with one particular company that's developing these products, and they're not yet available for demo. But what I would say is they're coming very quickly at us, and I think it would be very worthwhile sitting down and doing a workshop with us and our partner here. It's a household name company, and they can take you through what they're designing, what they're targeting, what size, what scale, and what timelines. And I think that's probably the best way to set up that discussion, and they can take us through their product development timelines.
So Jay, I was really curious about your slide on the copper production and the implications associated with that, and you all touched on that later in your presentation as well. And to me, it was kind of interesting because it almost looks like we can't produce enough copper to meet the long-term demands associated with meeting net zero requirements, plus everything else that's going on, and it has cost implications associated with it as well. So to me, it just sort of further emphasizes the need to look broadly at what some of the other options are, like HTS line and things like that. I think it's going to require a lot of solutions beyond just what we've traditionally been using. But I've been reading more and more about that. And then you also talked about we're having supply chain issues all over the place associated with getting transmission built right now with transformers and demand for copper wire and things like that. So I think it just emphasizes the need to look more broadly beyond what we've been used to for so long now.
I think that's a really good point, Larry. And I think it's also just worth remembering that you know, as we stare down the barrel of the gun, if you like, at the future that's coming at us, you know, it is really good to be, and I'm really glad to see so many people on this webinar, because I think it's very important to be getting ahead of technologies like HTS now and getting to understand them now, rather than when it's kind of too late and you're under huge pressure. So I do say, like, to people, I think it's a really good time to be looking at this project and looking at this technology and how you can integrate it into your grid today, and very much with one eye on that future as well.
And the only thing I'd add there is that we have the opportunities now with some of this IRA funding and some of these DOE announcements to really look into this technology in a way that maybe it wasn't appealing to before. And so we're happy to continue that conversation with anyone on the line who might be interested.
Yeah, well, we're still getting questions coming in, but we're really at the top of the hour. We're going to have to bring this to a close. So I would suggest that people continue these discussions with you all directly, and we'll provide that information. But Bud and Marie and Jay, I want to thank you for a really interesting presentation that has sparked a lot of interest. For our viewers, as we bring this to a close, I just want to comment that we're going to be continuing this wires technology, advanced technology webinar process into next year. And our next one coming up on January 17th will be from 2 to 3 o'clock in the afternoon, and that'll be with AmpJack. And they're going to focus on hydraulic system technology that's used for raising transmission towers. I think there's going to be a really interesting presentation as well. So thank you again for doing this presentation. It was terrific and very informative. And with that, we're going to go ahead and bring this to a close. But thank you, folks from MetOx, for your presentation today.
Thank you, Larry.
Thank you so much, Larry.
Thank you. Bye.
Bye now. Bye now.